All right, chums, let's talk about Chapter 6, Astronomical Instruments. We got a picture of Hubble Space Telescope up here, floating around the Earth. Talk about telescopes today, the different instruments and detectors that make them, and radio telescopes, and how we see light beyond Earth's atmosphere, and what's coming down the pipe. Okay, so this is a pretty cool picture here. The main thing we're going to talk about here is how we use telescopes to see different parts of the universe. And there's different telescopes for different types of radiation. So we saw in last chapter that visible light is just one part of the electromagnetic spectrum, and that comprises gamma rays all the way to microwaves, infrared and UV light and everything, and they all come from different mechanisms. And by studying that light, we can figure out what's going on at the sources of the light. So the main goal with telescopes are to understand and measure all the different radiation, different types of radiation from a source. So we've got the Orion constellation here. There's this belt, arm, right? Okay. This is what it looks like in visible light, okay? And that's what you see with visible light. When you look out into the sky, look up, you'll see the constellation. That's what it looks like. You'll see Betelgeuse up here in the top left and Rigel in the bottom right. You've got the Orion Nebula here, the 3 stars there, okay? In the same image, but with X-ray, you can see that there's a very bright X-ray source there. I'm looking closely. I don't see any sort of belt. I'm really trying to make out a belt somewhere in here. I don't really see a belt anywhere. So I can't see the visible light. So some stars emit X-rays, other stars don't. But there's a large gap here where there's a bright X-ray source in the sky. I don't think that's Betelgeuse for sure. Okay, so then if we look at the same with a telescope, but only looking at infrared radiation, boy, there's Orion's, the nebula here is just glowing like a Christmas tree. And look at that up here and there, okay, which is somewhere up here. And then whatever this is, way out here, right? So there's a lot of good stuff going on. A lot of different gases there. So you can tell by visible light, just using your eyeballs and then switching to different wavelengths, you can see a lot more of the universe than you think. And that's what telescopes are designed to do. So we've got Stonehenge and Machu Picchu. These are basically places that people use to look at the sky and sketch what they were seeing, and just be able to measure where the sun and the moon and the stars and stuff are over the year. And telescopes work by collecting faint light. That's the main thing it does, is collect faint light, because most of the light is too dim to see. So what you really care about is the size of the telescope. The amount of light that gets into the telescope, the bigger the aperture, the more the light, and the better resolve you can make the image. Okay, so what they say here is a telescope that, with a mirror that's 4 meters in diameter, can collect 16 times as much light as one that's 1 meter. So that's because of this pi r squared relationship between the size of the tube, the circumference, and the area of the telescope. Okay, basically there's a couple different types of telescopes out there. The most common one is the refractor, which is what Galileo used and what you generally think of when you see a telescope. And it has a large lens here, and parallel rays, when they hit the lens, get focused like a magnifying glass, and they focus that light to a pinpoint. And then if you put your detector here, all of this light gets focused down to a point, and so it can collect a lot of the light and make it more intense at that point, which allows you to look at it a little more closely, or zoom in on it, or whatever. So like a normal a normal refractor telescope just has one lens up here, and it refracts the light down like that and like this, and then you'll put another lens here and puts it out parallel. So it takes this light that's you know, whatever the size of this aperture is, and focuses it down to now fit on your eyeball. So that's one way it takes light from one area, increases its intensity, and brightens the source you're looking at so that you can see it with your eye. It also zooms in on it a little bit, so you might be able to see a little bit closer of what you're looking at. Okay, but the main thing telescopes do are not to zoom in, but to collect light. That's the main goal. Okay, the other type of telescope is one where there's a mirror in the back of it. There's no lens here. It's just mirrors. So the light comes in, hits the mirror, bounces up to this mirror, and then bounces out to your eye. And it goes around that, and that's called a Newtonian reflector, or just a reflector. There's a big problem with optics, and when you buy a nice telescope, the nice telescopes can get around this issue, and it's called chromatic aberration. And the issue is when you have rays of light coming in. So let's say I have a red ray coming in and a blue ray coming in, and when it hits a lens, let's say the red ray and the blue ray are right on top of each other, and when they hit the lens, they both get bent. Except the blue ray and the red ray, when they get bent, they separate a little bit. And so you end up with seeing a little bit of a rainbow, or a little bit of separation of light. The colors split, and so your image is a little bit blurry in the color spectrum, and that's called chromatic aberration. So you have to fix the lens a little bit, add a second lens to get around that issue. And they call them achromats, and there are additional lenses you can put on your telescope in order to see what you want to see. Okay, so the telescope here, the reflector, there's your prime focus, and then right there's your Newtonian focus and a Cassegrain focus, boom, out the back. So the Cassegrain system, if you're going to buy a telescope and you got a little bit of money to spend, you want to get a Cassegrain. They're generally the best all-purpose telescopes. If you're on a budget, definitely you want a Newtonian telescope. They're a little bit bigger and cumbersome to carry around, but they're a good deal. Okay, there's a choosing your own telescope here, so read through that just to help you understand the different characteristics. Okay, telescopes today, this is pretty cool. The Large Telescope Mirror. This is the Very Large Telescope. And so there's a very nice mirror there. Now they're making telescopes where, you know, this might be one of the mirrors, and they break it up into like several mirrors, and then it looks like there's, what, 7 mirrors here, but it all comprises one giant optical system. And these are some different telescopes. The Extremely Large Telescope, it's being constructed now. It's in like a 4-story building. It's crazy. It's huge. Let's see, we've got some others here. Yeah, so the SALT telescope, big aperture. This is a very big telescope in the Canary Islands, 10-meter telescope. A lot of good telescopes out there. Yeah, so check these out. This is the Palomar 5-meter reflector. Look at this thing. It's absolutely massive. The light comes in up here and bounces around and comes out, and it's just absolutely massive. Here's another one. The light comes in, boop, boop, shoots right out the back to the detector. Very, very cool. Gemini. Okay, so here you go. This is the 10-meter telescope in Hawaii at the Keck Observatory, and you can see that the mirrors are actually segmented. So it's easier to make one of these mirrors than a mirror that big. So they make all these little segments and put them all together, and then that can make a very large telescope. Okay, we've got some history here. The world's largest refractor telescope is in Wisconsin, actually. so you can go visit that if you're bored. The Yerkes refractor. How does it say where it is? Yeah, it should. Blah, blah, blah. Yeah, I'm pretty sure it's in Wisconsin. It doesn't appear to say that here. Anyway. Okay, observing sites. So here's a good thing about observing. You want to be obviously far away from light pollution, so far away from cities. You want to be in peaks, so the ones in Hawaii are ideal because it's surrounded by oceans, so it's completely pitch black around there, high up in the mountains. So you get higher in the air gets thinner, the skies get clearer, so that's where a lot of places are. What you want to avoid is a place that has a lot of weather, so you want to go somewhere where it's clear at least 75% of the time so you can get good observing. And you want to be high up to get through as much of the atmosphere as possible, so you want dry sites, which are found at high altitude so that you don't have a lot of humidity blurring the images. Yeah, you want to be away from cities, and you want to avoid things called bad seeing, which is the term when the air is turbulent, which obviously you want to avoid if you're flying in a plane. You don't want that turbulent air, like flying into Denver every time. So when the seeing is bad, images of celestial objects are distorted by this light. Okay, so the best observatories are high, dark, and dry, which is why you find them in Chile, in Arizona, in the Canary Islands, in Hawaii, and in these areas. So there you go. Way up in the Atacama Desert, and that's the Very Large Telescope. I mean, that's just amazing. Way up in the middle of nowhere. Okay, so the resolution of a telescope, just like, if you got an iPhone in 2010 and then you got an iPhone now and you take two pictures, one of them's going to be way clearer. That's because the resolution goes up quite a bit over time. And that's just the pixelation of the telescope. And the better the pixelation, or the lower the pixelation, the better the picture quality. There's a reason that Hubble is the only visible telescope in space. We keep building these telescopes on Earth because, well, it's a lot cheaper to have a telescope on Earth. But we've come up with something called adaptive optics. And by we, I mean human people. I'm also human, so I'm a we. The adaptive optics are a way for the telescope to cancel out the effect of the atmosphere blurring, which is kind of amazing. So what they do is you have your telescope, and if you've ever seen a time-lapse image of a telescope looking around at the sky, occasionally you see this laser beam shooting out into the sky. And what that laser beam is doing is it's shooting a laser out, and then there's a detector to measure the reflections coming back. And then based on the reflections and where they happen and what the laser looks like when it comes back and how polarized it is and other things it can calculate the path of the laser as it traveled up, and then sort of reverse that as the light comes through the sky from space and hits the telescope. The telescope can sort of change the focal length a little bit of their lens to accommodate that. And so here's a picture of Jupiter. This is taken from the ground. So this is a ground-based telescope at the Very Large Telescope in Chile, and they use adaptive optics. And this is infrared light to remove the atmospheric blurring. So you have this really clear image of Jupiter, and you can see the really cloud bands and just storms everywhere. That's an amazing image to take from the ground. Okay. So visible light detectors. So these are just examples of the devices that actually measure the light. So how does a telescope actually detect light? It's using something called a CCD, which is what are in SLR cameras, digital SLR cameras, and they're designed to measure photons. That's what they do. This is pretty cool. With an infrared camera, you can see right through the plastic bag and see the infrared radiation that's coming off the guy and going right through the bag. That's kind of amazing. Astronomers can know all your secrets. Okay, so there's, yeah, spectroscopy, we talked about that. If you send light through a slit to make it nice and vertical, and then send that light in through a prism here, then you can split the light into its constituent colors, and then that can give you the spectrum that you're looking for in order to see the what the element is made out of. Okay, so normally when we think of telescope, we think of a you know, tube, and the light comes in, and then you look out the back of it or something like that, and that's a telescope. And we're looking at visible light or something else. Well, there's also radio waves and microwaves and X-rays and gamma rays and all sorts of things. So there are other telescopes that look like this. They look like giant satellite dishes. And just like the satellite dishes in your backyard for satellite TV, these things focus radio waves, okay? And here's an example of a radio observations from the VLA, which is a interferometer, or a yeah, there's like, I can't remember how many, several telescopes all in a row, an array, if you will, of telescopes, and there might be a picture of it here, but of Cygnus, okay? And basically it's just showing you that there's a lot going on. Whatever is there is shooting out streams, right, of high energy jets, and then it's, you know, kind of turbulating here at the end. So you can't see that in visible light. You can only see that in radio, and look at that. I mean, just amazing. Okay, so I want you to just think about the fact that telescopes don't have to look like telescopes. This type of telescope, a radio telescope, is up all day. You can make observations all the time. The sun doesn't mess with it too much in that range of wavelengths. So here's some radio dishes around the world you can look at. So we'll talk about ALMA a lot, and we'll talk about the VLA a lot, and we'll talk about the VLBA a lot, which includes the telescope here in North Liberty, just north of Iowa City, and some other stuff. Okay, so interferometry is, there you go, there's ALMA. This is the Atacama large millimeter / submillimeter array. And what it is instead of building one giant telescope that's, you know, that big, they just build a bunch of little guys and set them up around to sample the radio waves, and then when a radio wave comes down and washes over the array, they all see a part of it. Okay, they all see the wave as it comes through, and then they all work together to get the signal. Okay, so and then the VLBA, you can see there's the telescope in North Liberty, Iowa. This is a, you know, almost a globe-spanning array, so that it can measure radio waves that are extremely long wavelengths. And if you remember, the image of the black hole was taken with the Event Horizon Telescope, which is basically these together with ALMA, together with every other telescope, and there's one down in Antarctica, and then that whole basically turns the whole globe into a telescope, and that's how we were able to see the event horizon of a black hole for the first time, which we'll talk about later. Okay, so radar astronomy. The biggest radio dish in the world is the Arecibo Observatory in Puerto Rico, and it's a pretty amazing facility in the middle of a caldera, and I think China's building a working on, or they might have built it already. I think they're trying to find staff to work there, but it's in the middle of nowhere in China, so they're having trouble getting qualified people. But anyway, it's a radio telescope, and so one of the things Arecibo is looking for is extraterrestrial life, signs of extraterrestrial intelligence, or non-natural signals from space. Okay, so in order to get outside of Earth's atmosphere, we have to put some telescopes higher in space. So here's a observatory which is on a plane, and the plane goes high up in the atmosphere to get through as much as possible, so that those wavelengths can make it through the sky. Okay, and this is pretty cool. So Spitzer is an infrared telescope, and in order to see those infrared signals, you gotta get above the atmosphere. So this is the Flame Nebula, Cassiopeia A, Helix Nebula, which is pretty cool images. But again, you can't see most of that light from the ground, so you need these telescopes in space. The next telescope for infrared imaging to go up is going to be the James Webb Space Telescope. And the thing about the James Webb Space Telescope is it has to be perfect because it's going to be out in the middle of nowhere, basically, really, really, really far away. So there's no chance that we could fix it. If something goes wrong, it's just going to be out in between the Earth and the Sun somewhere. Okay, Hubble is a space telescope. It's up in space above the atmosphere, so we put it above the atmosphere because we didn't have the computational power to do adaptive optics at the time. And this is a very fundamental picture in astronomy that Hubble took. This is the ultra-deep field. Every point of light in this image is a whole galaxy. So if you look really closely at each of these things, you can see that this image is nothing but galaxies. And it's a pretty amazing, if you can get the super high resolution version of it online and zoom in on there and you go, whoa, this is crazy. Okay, and then on the opposite end of the spectrum, we've got UV and X-rays and gamma rays, which don't come to the surface. So Chandra is one of the X-ray observatories in space. This is a nice picture of Chandra here. And it sees X-rays. And then, like I said, Spitzer, the gamma ray space telescope, the Fermi gamma ray space telescope, that's one that measures gamma rays. Integral is another. Kepler, that's a visible light, so that's looking for extrasolar planets. And Gaia here is looking at every star in the Milky Way, trying to get a very good map of it. So that's a really cool experiment. Go check that out. Okay, the future of large telescopes. All right, so this is the future one, James Webb Space Telescope. If this gets out there, get ready to have your mind blown, because that's going to lead to some pretty amazing images. We'll be able to see even further into space than ever before. It's going to be wild. Okay, and yeah, the extremely large telescope. This is a big telescope, 40 meters across. That's half a football field, almost. So that's a big mirror. And that's the end. Okay, so again, make sure you know adaptive optics, the aperture, what a CCD is, chromatic aberration, the detector is the CCD, what sees the light, your eyepiece, what you look, the focus of the telescope, interference is the way light mixes, interferometer is when you put two telescopes together, and so yeah, you can combine these two together. An array of telescopes, right, or an array of interferometers is, you know, multiple telescopes together. The reflecting and the refractor, make sure you know the reflecting telescope has a mirror in it. The refracting telescope refracts light using lenses. The resolution is the quality of the image, and the seeing is how steady the Earth's atmosphere is. And what is a telescope? It's just the thing that does all the stuff. Okay, see you guys later.